symbol for dot product is a dot. So you do have to be careful that you don't think that's multiplication. You should know it's not multiplication because it doesn't make sense to multiply vectors. There's no reason to multiply vectors. Okay. How you find the dot product. So this is the symbol telling you when to do it. So let's say you had a vector A1, A2, and another vector B1, B2. There's kind of a formula behind it, but I don't really think of it as the formula. What you do is you multiply the horizontal components together. So for me, that would be A1 times B1. Then you multiply the vertical components together. So that would be A2 and B2. So this is going to give you a number. That's going to give you a number. And then you add those together. And whatever they add up to is your dot product. So a couple quick examples. If I wanted the dot product between 4, 5, and 2, 3, I would multiply the vertical components, 4 times 2. I would multiply the vertical components, 5 times 3. Add them up, and their dot product would be 23. So as long as you know where that comes from, just some arithmetic. Multiply the horizontal components together, multiply the vertical components together, add them up, and that is what we refer to as dot product. Alright, now that you see how to do dot product, we really ask you to do 2 of these a lot, but there's 3 good applications for that. So one is, if the dot product of 2 vectors is 0, so if you did this process and you get 0, then those vectors would be perpendicular. So they would touch at a 90-degree angle. But with vectors, we don't usually say perpendicular. They have a fancier word with it, which is orthogonal. But orthogonal still means perpendicular. They touch at a right angle. So that is one good application of dot product. Dot product 0, the angle between them is 90. If it's not 0, the angle between them is not 90. Same on many aspects. Okay, so an example of one that is and is not, and how you could just how you work. So I would find the dot product of this, multiply your vertical components together to get 12, or horizontal components. Then multiply your vertical components to get negative 12. Add those up, you get 0. And so now, without sketching down, without doing any precise measurements, I know that yes, they're orthogonal, and my y could just be dot product is 0. Again, you could sketch this one and you could sketch this one and you could have them started at the same time. And looking at them, it should look like a right angle. But even though they look like a right angle, it's hard to know for sure. And this is a very quick way to know for sure that it's exactly 90 degrees. Okay, so here's an example of one that should not be. Multiply the horizontal components to get 0. Multiply the vertical components to get 8. Add those up, and the dot product is 8. And if the dot product is not 0, they are not orthogonal. Okay, so there's one application. That'll come up again before we're done today. The second one, which I honestly don't use much, but it's nice for you to see that it works, is in finding the magnitude of the vector. So same thing you should have done for me on today's quiz. So on the left column, we're going to do it the same way we've already talked about, and on the right column, I'll show you how a dot product can do the same thing. Okay, so if I asked you to find the magnitude of 3, negative 4 on today's quiz, you probably should have sketched it, like 3 down 4. You see that you have a right triangle, so you can use Pythagorean theorem, or in this case, Pythagorean triple. But you end up taking the square root of the legs squared plus the legs squared, the square root of 9 plus plus 16, which is the square root of 25, which is 5. There's nothing wrong with that. You can still keep doing that if you want to. But a different approach to the same thing is you can take the square root of the dot product of a vector with itself. So I could take this vector and the duplicate of that vector, and I could find its dot product. So horizontal components together make 9. Vertical components multiplied together make 16. Dot product tells me to add them up. So if you want to go that route, that's great. Just don't forget the square root. Notice you get the same thing. And notice how the work starts to match up. So if you prefer that, by all means, use it all the time if you want to. But dot product of itself and then square root. So there's a second application. And let's practice that once more, just to be sure that you see the differences there. Because that one was a Pythagorean triple, it's a little bit easier. Okay, so the way we've been doing it for the last couple of classes, just sketch it. You can see that you have a right triangle, and then from Pythagorean theorem, square root of leg squared plus leg squared will give you hypotenuse squared. That's still fine. I'm not telling you to not do that. But I also want you to see that if you took that vector, negative 2, 5, and we found the dot product of that vector with itself, so multiply the horizontal components together to get 4. Multiply the vertical components together, you get 25. Dot product, you add those up and you get 29. And then you just have to remember to take the square root. In some ways, I mean, the arithmetic behind it basically the same, but in some ways that seems a little bit easier or something. So just know that that's a possibility. Alright, I don't use that one too much, honestly, but the third one is very useful, and this one has a formula that you will need to know. So lately, several things we've done have not required you to memorize formulas, and part of that is because you don't need it for a couple of years, not in calculus AB, but maybe in BC or Cal 2, so you're going to have to re-memorize them anyway. Things like the law of sines and law of cosine doesn't really come up in calculus, so we don't really care if you memorize the formulas or not. Although I will tell you, we had a meeting yesterday, good period, and we pretty much decided that we thought that was a mistake because we're finding out that law of sines and law of cosines is being put on the ACT on a regular basis, and they're not giving you the formula. So I'm sure you know law of sines, that's a basic one, but before you take the ACT again, it sounds like you should memorize law of cosines. Okay. Just because we've been giving you some formulas lately, unless I tell you ahead of time that you don't even know what you need to assume that you do. You've got to memorize that. And it says the cosine of the angle is equal to u times v. Is that what this says? Multiply vectors? Right. Multiplying vectors doesn't make any sense, and that's how you're sure that it's referring to dot product. Divided by the magnitude of one of them times the magnitude of the other one. Now you can multiply here, because this is just a number and that's a number. You can multiply numbers together, you just don't multiply vectors together. Okay, so let me show you 3 ways, or really 2, and then kind of a fancy case, I guess. So I can sketch these 2. Right 4, up 3. Just like that. And then if I tried to draw the scale, right 3, up 5, this formula helps me figure out what's the angle in between those 2 vectors. Okay, so part of the formula requires us to be able to do dot product. So multiply the horizontal components together, get 12. Multiply the vertical components together, get 15. Add them up, and you get dot product. No big deal there. Okay, slow down a bit to find the magnitude of this. So you've got two ways to do that now. You can sketch it, Pythagorean theorem, like you've been doing, or you can do the square root of the dot product of the vector with itself. I've kind of got these already sketched. So I can see this one has a magnitude of 5. Let's say 3, 4, 5 triangle. And this one is 3, 5. So is it also a 3, 4, 5? I thought 3, 4, 5 is one of the Pythagorean triples, though. Your hypotenuse has to be your biggest side. So if 5 is not your hypotenuse, this is not 4. That doesn't make sense. So in that case, we would need to do leg squared plus leg squared. Okay, I'm not too concerned with how messy that is, or even if the square root of 34 breaks down, I don't even care. I'm not even going to do that. Because I'm going to need my calculator in a second anyway. If this is what the cosine of the angle equals, then the angle will be the inverse cosine of that stuff. And you need to be in degree mode. And you probably need to put in parentheses here. So it'll be part of what you need to practice next time, making sure that you understand how to type it in. And my calculator tells me the angle between those two vectors would be about 22 degrees. I'm going to have you practice this on the third one, so you don't need to take the time for it. And with my very terrible sketch here, 22 degrees seems reasonable. That looks like that could be a 22 degree angle. Okay, so let me show you another one, and I'm going to ask you to try the third one. Okay, so the formula says the cosine of theta is equal to the dot product of the vectors. The dot product is multiplying the horizontal components together, getting a number, multiplying the vertical components together, getting a number, and then adding those up. And then dividing by their magnitudes multiplied together. So you have to seek out this magnitude with either of the two ways we talked about. One's a little bit easier, 3, 4, 5 triangle. Okay. This one is like 6, 10. What does that look like? That's not supposed to be a good question. What's this one? Okay, well, what's the square root of 136 breakdown? What's square root of 34? No, not quite. Yeah, there you go. It would be 2 square roots of 34. Yeah, compare these. If this side's twice as long, and that side's twice as long, then proportionally this side's going to be twice as long. And knowing that this was the square root of 34, I can cheat to know that this is going to be 2 square root of 34. It's not that you have to recognize that. You could have done Pythagorean theorem and stuff like that. Okay, so 10 square roots of 34. Alright, that's what cosine theta equals. So if you just type this in your calculator, you're going to get a number between 1 and negative 1, but probably not the angle. It would be an extreme coincidence. You still need to do inverse cosine. And type it in correctly with some parentheses to make sure it does the order of operations the way you expect it to. Specifically, these are grouped together. My calculator is telling me that's about a 5.906 degree angle. And I didn't draw the vectors on top of each other like I did the last time. If you can try to imagine, if I put this vector right here, the angle between this and this would be very, very small. In fact, almost 6 degrees. That's what that formula is from. Okay. I want you to try this on number 9 before we discuss it together. So, find the dot product, find the magnitudes, plug it all in, see if you can determine what angle would be between those two vectors. Not having to go from let's check your work. So I have a feeling you know if you did it correctly or not once you saw the answer in the end. Alright, so if I try to use our new formula here, cosine of the angle will be equal to the dot product, which will be 12 plus negative 12 over the magnitude of the first one. Be the square root of 13 times the magnitude of the second one would be the square root of 36 plus 16, which would be 4052. So my calculator, I'm going to read inverse cosine. What? I'm going to throw it in the calculator anyway. No. Like, I was about to say that's my final answer. Yeah, that's not. So, this, I guess I could multiply the square root of 13 times square root of 52. But my calculator is going to deal with it anyway, so I'm not going to bother and maybe mess it up. And we did all of this. Actually, no, you didn't do all of this. But, so my calculator tells me it's 90 degrees. So let's backtrack a step. 0 divided by anything is what? 0. So you're asking your calculator what angle has a cosine of 0, and that's 90 degrees, right? So even if I made a mistake here, or whatever, it's still going to come out right. And even before that, you should have hopefully stopped really early. Because the first application, dot product. If your dot product is 0, we call them orthogonal, but it just means that there's perpendicular, there's a right angle between. So he said a dot product is 0, so there's going to be right angle. So you didn't really have to jump through all the hoops of the formula. It didn't hurt you, but it's just not necessary. Okay, some of the questions we will ask you will be to classify something as a vector or a scalar. Scalar is just a fancy word for a real number. So 5 is a scalar, 100 is a scalar, and 50 is a scalar. And then, so it's either going to be scalar or it's going to be a vector. Well, vectors are things that look like that, or that. So scalar just means numbers, real numbers. Vectors look like vectors. You need to tell the difference. So we're not going to practice that stuff today. We're going to finish the last page of the notes, but you'll have questions where you do some work and you get a number answer, and you'll have to classify the scalar. Or you'll do some work and you get a vector as an answer, and you can classify it as vector. And that's on the list. I'm not going to say. Alright, so our two applications. If you take a physics class, or if you've taken a physics class, I'm sure you go much more in depth with work. But work is just a way to describe how much energy or force has to be done in order to get something done. And so the formula, another formula that you have to know here, is going to be that work is force times distance times the cosine of the angle. So it's force. So like something that weighs 1 pound doesn't take much force to move. Something that weighs 1,000 pounds takes a lot of force to move. It's more work to move something that's 1,000 pounds than 1 pound. So that's part of our equation. D is distance. So it's a lot more work to move something 1,000 feet than it is to move it 1 feet. So it keeps up with that. In our case, we're talking about moving things horizontally. So there's an efficiency behind it too. So the angle that you move relative to the ground can be very efficient or non-efficient. So like if you were, the classic example is like mowing the lawn. So imagine if your handle was like almost straight up and down. It was like a 98-degree angle. And you're pushing straight on the handle. Well, almost all of your energy is just pushing the lawnmower to the ground. That doesn't really help you mow the lawn very much. That's not a very small part of it. You would look kind of funny, but if you got on the ground and you were parallel with it and you pushed it, then all of your energy would be to mow the lawn. So that would be much more efficient. So our calculations, cosine of that helps us determine how efficient it would be. Now, since we don't spend much time on this, again, there's not really any variation for these. We'll tell you the distance. We'll tell you how much force has to be applied. And we'll tell you the angle that it makes with the ground. So as long as you know that work is force, I would like you to write the units there too. 55 pounds times the distance, 100 feet, times the cosine of 40 degrees. That's all they'll expect you to do. 55 times 100 times cosine 40 tells me the work that would need to be done to make this happen would be 4,213.244. And the units, since this is pound times heat, we like to call these foot pounds. And I know it's very similar to a joule. Those of you that do physical and joule. I think there's a slight difference between foot pounds and joule. And I never remember, I have to look it up.
I think it's because like physics needs to be
yeah,
so that's why.
But you don't need to know. Just keep up with the needs there. I think it's always going to be different. So notice how it would be different if I still wanted my launch just as long as it was. I still got the same mowers, but still takes the same amount of force to move it. But let's say I adjust the handle a bit, and now I'm saying the handle is at an 80-degree angle. That could be better or worse for you. But as far as our questions go, 55 pounds times 100 feet times the cosine of 80 degrees. You might want to sketch a picture to help see that. I'm actually pretty bad at sketching. You know the formula, we have to give you exactly what you need. Calculator does this. So it's not a big deal. It is good for you to understand how all that kind of comes together, though. Okay, the last type of application problem will be this is the one that was, and you really kind of know the math behind this. You just need some practice setting up the pictures. So it's about putting an object on a hill and trying to figure out how much force is going into the hill perpendicular, and how much force would you have be required to keep the object from rolling up. So all that can really change about these questions is what I put in the blank here. So let's pretend this question's about you. So how much do you weigh? Nobody wants to share how much they weigh? I'm going to guess you weigh 140. Okay, let's say you weigh 140 pounds and you stand on a hill that has a slope of what? 60 degrees? That's like a cliff. All right. 15. Put that too. Okay, so here's our picture. Again, finding these is actually going to be really easy if you get the picture right. So here's the ground. Here's my hill. The slope of the hill is 15 degrees. And then here you are on the hill where your elephant or whatever, doesn't matter. Okay, so the first vector in this picture is your weight. When you say you weigh 140 pounds, that's you standing on the scale straight down. And then what you need to see is that if you're actually on the hill, some of your weight is pushing into the hill, perpendicular, and we will call this the force perpendicular, and that's one of the things we like to ask for. But some of your weight is trying to push you down the hill, which most people refer to as the force downhill. Now, if you know how much force is pushing you downhill, then that's exactly the same amount of force that you got to exert to keep from rolling downhill. So it's really finding this magnitude is the same as answering that question. Okay, so within this, luckily, this vector that's called the force downhill has a vector parallel to it right here that we call the force parallel, and we call it parallel because it's parallel to that guy, and it's equal in magnitude. And if these are parallel, and this is perpendicular to this, then this has to be perpendicular to this. And so what you start to see is you've got a right triangle. You know one length, or one magnitude in this case, 140 pounds, and you're interested in the other two. Well, the information we have at USED is this angle. If this is 15, you could do a bit of an angle chase. This is 90. So this would be the complement of 15. That would make it 75. And then if these three angles make 180, and this is 90, these have to add up to 90. So what's that make this? So you can do that, but this angle ends up being the same as that angle. Okay, so I'm going to redraw my picture now. I really don't care about any of this anymore except my triangle. Here's my weight. Here's the force perpendicular. Here's the force parallel. That's the right triangle. And with a little bit of work, we can figure out that angle is 15 degrees. This is supposed to be a right angle. Right. Alright, well, you want the force perpendicular. You want the adjacent side, and you know the hypotenuse. So cosine of 15 equals adjacent over hypotenuse. And I will ask my calculator, what is 140 cosine of 15? And it tells me it's 135.230 pounds. Now, to be fair, I don't know why you would care how much force you're pushing into a hill, but it could be a piece of glass you're walking on. And in that case, you would need to make sure that the glass was rated for more than 135 pounds of pressure. That was it. Okay, and if you wanted to find the force parallel, you would be trying to find the opposite when you know the hypotenuse. So that would just be a sine equation. Well, opposite over hypotenuse. So the force parallel, I will ask my calculator to compute 140 sine of 15, and it tells me that it's about 36.235 pounds. But the force parallel, the magnitude of that is equal to the force downhill. So just naturally standing on that hill, you've got about 36 pounds of pressure trying to push you down the hill. So that's also the force you would have to push back to keep yourself from falling down. If you want to stay put, you've got to put in the same amount of force. So steeper hill, you would have to exert a lot more pounds to keep yourself from falling down. If this was only 1 degree, you wouldn't have to exert near as much. So let's practice drawing the picture one more time. All we're going to change is the weight and the angle. Okay, so 140 might have been you. How much do you think of whatever? How much of your pet weight? 15 pounds. Is that a dog? Okay, 15-pound dog. And we're going to put him on a cliff. Okay, not more than 90. Okay, you do it. It's not my dog, I don't care. Alright, so we sit at a hill. I'm not going to try to make it look exact. It's going to be too hard to keep up with. But this is 89 degrees. So I'm running a hill with the dog. His weight is straight down, not straight into the hill. And then you have to understand that some of that 15 pounds is pushing into the hill, force perpendicular, and some of that 15 pounds is trying to push him down the hill, force downhill. Well, the force perpendicular is obviously perpendicular. The force downhill is equal to the force parallel. So this other vector that's parallel to this one. So if we can find the magnitude of the force parallel, we actually have the magnitude of the force downhill. And how much force is trying to push you down the hill is how much you would have to exert to not go down. Okay, this one's about a piece of glass, but all the same thing. So, as of right now, I have a right triangle that I only know one side of, So Pythagorean theorems off the table. I don't have any information for that. But I could almost do a Stochastic equation if I could just get an angle, one of these acute angles. So these two angles always end up being the same. But it's bad to memorize that because you're not going to remember that too much. But you could say if this is 98 and this is a right angle, this would have to be 1 degree. And if this is 90 and this is 1, this is 89. So you can find it easily enough. And if your picture is too hard to see, I would suggest that you stretch your right triangle out to the side. Because now I don't really care about any of the rest. Now I'm ready for Stochastic. Cosine allows me to pair up adjacent over hypotenuse. Okay, so since this is a very steep hill or a steep piece of glass, what do you anticipate this number to be meaning? Should be close to 15, right? Because then the cosine of 91. But using our calculator, cosine of 90 is 1. Cosine of 90 is 0. So this is 15 times almost 0. So my calculator tells me that is only about 0.262 pounds. So this is because if I'm using this angle, that's the adjacent side, the over cosine. Now if you're using this angle, you'd have to do more work to find that angle. But then yeah. So to me that makes sense. If you're standing on a super steep cliff, very little of your weight is going into it. Most of your weight's trying to pull you down. Okay, so the force parallel, which will be the opposite side, is equal to the force downhill, which is also equal to the force you have to exert to not go downhill, which this is asking, and that will be equal to the sine, or it can be found by doing the sine of 89 and doing opposite over hypotenuse. So 15 times the sine of 89 degrees is what the force parallel would be. Okay, now this one should be close to 15, right? Because the sine of 90 is 1. The sine of 89 is almost 1. So almost 1 times 15 is 15. Almost, he has to exert almost as much force as his entire weight because that goes so steep. Basically, got to support himself completely. Okay, if you practice doing the pictures, after you get some practice there, it just ends up being a cosine equation of the math behind it, but you do need some